Okay, we are given information from a bomb calorimeter where hydrazine is combusted. Okay, so that means it's reacting with oxygen. And it's giving us information about how much water was placed around the bomb and the temperature change of this system. And it wants us to calculate the heat of combustion for 1 mole of hydrazine. Now, hydrazine, as it says, is rocket fuel. And when it reacts with oxygen, it will produce nitrogen gas, which I don't expect you to know, I'm just telling you this, and water as the products. And if we balance it, we can balance it by putting a 2 right here. Now this reaction would be balanced for 1 mole of hydrazine. So if we knew the delta H for this reaction, that would be the heat of combustion because it's called a combustion reaction. So that's our goal here, is to determine the delta H for this balanced reaction. Now they did not place a mole of hydrazine in this bomb. They only put 2 grams, which is far less than a mole, into the bomb calorimeter. So what we're going to do is figure out, first of all, how much heat is produced when 2 grams of this hydrazine reacts. And then we'll be able to translate that into how much would be produced when 1 mole reacts. Now, anytime you're dealing with calorimetry, what you want to do as a starting point is to know that the heat of the system equals the negative the heat of the surroundings. That's the starting point for any type of transfer of thermal energy. Now the system is my reaction, so that's what I'm going to determine, the heat of the reaction. The surroundings is made up of 2 things. You've got your bomb calorimeter, that says BAM, but it's supposed to be bomb. And you've got your water that surrounds the bomb calorimeter. The bomb calorimeter can be further broken apart into the heat capacity of the bomb times a change in temperature, and that's given to me. The heat capacity of the bomb is 927 joules per degree Celsius. The water can be further broken apart into the mass of the water, the specific heat of the water, and the change in temperature. So we can place in there the information that we know. The C is equal to 927 joules per degree Celsius. The change in temperature, well, let's go ahead and calculate the change in temperature. It would be final temperature, 32.19, minus the initial temperature, 25.15, and that will give us a change in temperature of 7.04 degrees Celsius. I can place that right here. So this is times 7.04 degrees Celsius. The mass of the water is 1,000 grams. The specific heat of water is 4.184 joules per gram degree Celsius. And the change in temperature of the water would be the same as that of the bomb, 7.04. So if we multiply all that information out, what we will obtain is that this is equal to a negative 35,981 joules. Or to 3 significant figures, which is all we can really know this. To 3 significant figures, that would be a negative 36.0 kilojoules. That does not look like a 7. I'm going to fix that right there. Okay, so there is the amount of heat that would be generated when 2 grams reacts. So let's write that ratio. This is negative 36.0 kilojoules for 2 grams of N2H4 reacting. Now remember, we don't want it per grams. We want it per mole. And we want it for 1 mole because that's what the balanced equation is. So when we put in the molar mass of hydrazine, which is 32.06 grams per mole, we will be, as we see here, left with the units of kilojoules per mole of hydrazine. I suppose I ought to be good and put N2H4 here and N2H4 here, so we have things perfectly canceling. And that will give me the value of a negative 577 kilojoules of heat released for 1 mole of hydrazine. And so now we can say with certainty what the value of the delta H for this reaction is as balanced with 1 mole. This would equal and negative 577 kilojoules.